Section 5.3 Part 2. In the last video, we looked at matrices and we looked at different ways to determine if they are diagonalizable. So, let's review the diagonalization theorem, which we saw in the last video. If A is an n by n matrix, we say first that A is diagonalizable if and only if it has n linearly independent eigenvectors. Also, next, if A is diagonalizable, then the columns of P are the eigenvectors of A, and the diagonal entries of D are the corresponding eigenvalues. Lastly, we looked at if we have an n by n matrix with n distinct eigenvalues, it is diagonalizable. So, if we look at the last example we looked at in our notes, we wanted to find out if this matrix A was diagonalizable. And we came up with this characteristic equation here and found out that lambda was equal to 1, -7, and 3. And therefore, we deduced, since we have n distinct eigenvalues, that this matrix is diagonalizable. Now, using A minus lambda I, for each of our eigenvalues, we can find a basis for the eigenspace. And so, when lambda is equal to 1, we get V is equal to 1, 0, 0. When lambda is equal to -7, we get V2 is equal to -1/4, -1, 1. And when lambda is equal to 3, we get V3 is equal to 1, 1, 1. Well, of course, we do this by plugging into this A minus lambda I, plugging lambda into it, row reducing, and finding a basis for the eigenspace. So now, I want to look at if we make P, a matrix P, be the vectors V1, V2, and V3, we get this matrix P here, which is each column is the vectors V1, V2, and V3. So now let's actually revisit our diagonalization theorem. It tells us if A is diagonalizable. Now keep in mind, we found that it was diagonalizable in the last slide because it had n distinct eigenvalues. Then it tells us that the columns of P, which we just saw, are the eigenvectors of A, which is what we've just shown, which is here. And the diagonal entries of D are the corresponding eigenvalues. So what do we notice here? Our eigenvalues, -1, -7, and -3, are the diagonal, the entries along the diagonal for my matrix D. They correspond to their corresponding eigenvectors. And so, we saw in a slide from the last that if A is diagonalizable, then A would be equal to P times the diagonal matrix D times P inverse. And so we have P inverse here, and we take this by, you can use any kind of, you can do it by hand or use a math software, MATLAB, or any other software that you can use to find P inverse. And multiplying through, we notice that indeed we do get the original matrix A that we started with. So again, A we said was diagonalizable. And so the columns of P, we say here, are the eigenvectors corresponding to these eigenvalues, which make the diagonal entries of D. And finding P inverse, multiplying out, we get back the matrix A. So this proves that indeed this matrix A is diagonalizable. Now let's look at another example where A is equal to this 2 by 2 matrix here. So let's find our eigenvalues for this matrix. We're going to do that by finding the determinant of A minus lambda I. Doing so, we notice we get 3 minus lambda to b squared is equal to 0. Okay? And so we mentioned in class that lambda is equal to 0, lambda is equal to 3 is our eigenvalue, but we say it has multiplicity 2, which means it's occurring twice. So with lambda equal to 3, we can do a minus lambda. We notice we get this vector here, 0, 2, 0, 0. And we can clearly see, so we have our x1 and our x2, we clearly see that x1 is free, okay, and x2 will clearly equal 0. And so therefore, we get x is equal to the x1 times the vector 1, 0. So a basis for our eigenspace would be 1, 0. Now, again, let's go back to our diagonalization theorem. Our diagonalization theorem told us that A is diagonalizable if and only if it has an n linearly independent eigenvectors. So we notice we only have one eigenvector here. So therefore we can say, since A does not have two linearly independent eigenvectors, keep in mind this is a 2 by 2 matrix, so n is equal to 2, we can say that A is not diagonalizable. Okay? So therefore, we got to keep in mind when we have multiplicity, it may or may not be diagonalizable. We have to check to make sure we have n linearly independent eigenvectors. And for this particular example, we only have one, and since n is equal to 2, we can say A is not diagonalizable. Now, another thing we notice here is that we can clearly, we can clearly see, since this is a triangular matrix, that I'm going to have lambda equal to 3 with multiplicity 1, 2. So without using the determinant, because this is a triangular matrix, we already see that lambda is equal to 3. And so we can eliminate this step here. Now, also for this example, if we remember, there was a theorem that says if I have an n by n matrix with n distinct eigenvalues, then it's diagonalizable. And so this case, we noticed that we did not have n distinct eigenvalues. And so, but we cannot make the assumption that it's not diagonalizable until we go through this process to see if this part of the theorem holds. Let's look at the example that we did on the in-class assignment in class. Okay? And so for this problem, we were given this matrix D that had an H in it. And we were asked to find the H, given that the eigenspace for lambda equals 5 is two-dimensional, then what must H be? So we actually clearly see here, let's look, since this is our triangular matrix, we see we have lambda is equal to 5 with multiplicity 2, 3, and 1. So we don't have n distinct eigenvalues, so we cannot automatically say that this is diagonalizable. But let's do a little inspection. Since we know that it's two-dimensional, what does that tell us? That we will have two free variables. So when lambda is equal to 5, if we do minus d minus lambda I, we get this matrix here. And so row reducing, you don't have to put it in reduced row echelon, but at least row echelon. And I've put it in reduced row echelon. I see I have a pivot here, a pivot here, and a pivot here. Okay, so I already see that x1 is a free variable. But since we say that it is two-dimensional, that means that I have to have an additional free variable. And so since this here, we have this h minus 6. If we let h equal to 6, then this will be a 0 in this entry right here, which will mean that x3 will also be free. And so, for lambda, if we write a basis for this eigenspace, we get these two vectors here, 1, 0, 0, 0, 3, 1, 0. So we still see with the lambda is equal to 5, we have two vectors in our eigenspace. Okay, let's continue looking at this same example. So we've just found that when lambda is equal to 5, we have two vectors in our eigenspace. And we can do the same thing where we do our A minus lambda I for each of our eigenvectors. So for lambda equals 3, we get one vector in our eigenspace, 1, 1, 0, 0. And then when lambda is equal to 1, we get one vector in our one eigenvector, 13 fourths, 3, negative 1, and 3. So when we look at the span of these eigenvectors, we get this here. Now what do we notice here? Let's go back again to our diagonalization theorem. It tells us that if A is diagonal, not diagonalizable, if and only if it has n linearly independent eigenvectors. So we noticed that we had multiplicity 2 for our 5. Sorry. For some reason it's not letting me do this. Okay. We have multiplicity 2 for our 5. In the previous example, we saw that we did not get n vectors in our eigenspace. But here, since we know that that was two-dimensional, we notice that we do indeed have 4 independent eigenvectors. So therefore, in this case, D is diagonalizable. So for the theorem that A is an n by n matrix with n distinct eigenvectors is diagonalizable, the converse is not necessarily true. If a matrix is diagonalizable, that you will have n distinct eigenvalues, because in this case we notice that we have 3 eigenvalues, just 3 distinct eigenvalues. Now complete this reading assignment. What is a diagonal matrix? What ways can we determine if a matrix is diagonalizable? Given the diagonal matrix A, find A to the 4th. And lastly, is the following statement true or false? Explain why or why not. If an n by n matrix is diagonalizable, then it has n distinct eigenvalues.